All right, page A24, Appendix D. We want to review our trigonometry. All right, so to begin with here, remember that you can measure angles two different ways. You can measure them in degrees, as we did in lower levels of mathematics, but you can also measure them in radians, like we did last year in pre-cal. And so the equivalency that we used was that in one revolution of a circle, there are 360 degrees, but there are also 2 pi radians. Now, if we approximate pi as 3.14, we're saying that there are like 6.28 radians in a circle. So a radian is approximately 57 degrees. It's like 57.3 degrees. So you can see if we rounded that to 60, if you take 360 and divide it by 60, you're going to get 6 radians. And then because we were rounding up, you're going to have, a little bit extra. So that's where we get the 6.28 radians. We also more frequently divided both sides of that by 2 and used the equivalency that 1 pi radian was equal to 180 degrees. So the definition of a radian comes from if you had a circle, when your radius and your arc length are equal to each other, the angle that they subtend is going to be, that central angle is going to be 1 radian in size. So for instance, if this radius was 5 centimeters and this arc length was 5 centimeters, then that central angle would have a measure of 1 radian. So we can use that information to help us convert between radians and degrees and radians. So if we start with pi radians is equal to 180 degrees, the statement we had up here, and we divide both sides of that by pi, we find out that 1 radian is 180 over pi degrees. There's that same 57.3 that we talked about. So if I wanted to convert from radians to degrees, I could use that little formula right there. If I have 5 pi over 4 radians and I want to know how many degrees that is, here's that conversion formula that we just were talking about. I don't have 1 radian, I have 5 pi over 4 of them on the left side. So let's multiply both sides by 5 pi over 4 so that I can get the 5 pi over 4 radians I need over here. And of course, what I do to one side, I do to the other side. So let's simplify over here. You can see that our pi's would cancel each other out, and 180 divided by 4 would give us 45. So we would end up with 45 times 5, which is 225 degrees. Now, last year we had a shortcut for that. We said anytime that you had a radian measure that had pi in it, you could just replace the pi with 180, right? So if you did 5 times 180 divided by 4, you'd go straight to that 225. Okay, well then why do I need to memorize the formula? Well, what do you do if they give you a radian measure that doesn't have pi in it? Like if they had said, what is 3 radians equal to? Then I need this conversion formula because I would need to multiply both sides by 3 to be able to figure out what that is. I wouldn't have a pi to put 180 in for. Okay? What if I want to go the opposite way? I want to go from degrees back to radians. Well, we're going to start the same way with that statement that 180 is pi radians. Only this time we want to know what 1 degree is equal to. So let's divide both sides by 180, and we find out that 1 degree is pi over 180 radians. So I don't have 1 degree, I have 60 of them. So let's multiply both sides by 60 so I can get what I need on the left-hand side. And so over here on the right-hand side, we could simplify the 60 and the 180. And that would leave me with 1 pi in the top and 3 in the bottom. And of course, that's a value that we worked with incessantly last year that we already know. But that's a great example for us to use to see that that formula really does work. So there in the middle of page A24, they give you a list of some of the more common values that we had off of the unit circle. They're radian and degree equivalents. You do need to know your values off of the unit circle. I already gave you a unit circle to reference, but you do need to know the degree, the radian, the sine, cosine values off of that circle, and then be able to use that to get the other 4 trig values, tangent, cotangent, secant, cosecant. So all of those things we'll utilize this year. All right, bottom of page 824, they discuss a little bit more this relationship we mentioned up here about how the arc length and the radius and the central angle are related. They tell me that the central angle will be equal to the arc length divided by the radius as long as the central angle is in radians. Now, if you come back up here, remember that we said when r and a were equal to each other, theta was 1. Well, that makes sense if you're looking at this. If these two were equal, they would divide out to be 1, so we can see how that makes sense. We also could solve that equation for whatever piece we needed. Like, let's say they were asking me to find the arc length instead. Well, if I want to know what arc length is, all I'd have to do is multiply both sides by the radius. So we could say arc length is the radius times theta. If we wanted a formula for the radius, what would I do? What could I do to this guy to get a formula for the radius? Divide by theta, right. So the radius would be the arc length divided by the central angle. So example 2, maybe one of the easiest problems that we'll do all year long. So example 2 says, if the radius of a circle is 5, what angle is subtended by an arc of 6 centimeters? All right, so my radius is 5, my arc length is 6, and they want to know theta. So don't make it harder than it is. I'm literally going to use this cute little formula right here and throw 6 in for A and 5 in for R, and I get my answer. All right, for the B part, it says if a circle has a radius of 3, what's the length of an arc subtended by a central angle of 3 pi over 8? So they gave me the radius, they gave me the central angle, and this time they want the arc length. So if I'm looking for arc length, I could use this formula and just say r times theta. Now, theta does have to be in radians, so if they had given it to me in degrees, I would have had to convert it first, like we were doing up here, converting degrees to radians. Also, we want to always give the exact answer, not a decimal approximation, unless they ask me to give a decimal. If they ask me to give a decimal, on the AP exam, you will always give 3 decimal place accuracy, a minimum of 3. You can give more than 3, but you cannot give less. So that'll be our standard this year as well, that we'll always make sure that we maintain 3 decimal place accuracy. All right, over in the middle of A25, you see a couple of bold print terms, standard position, positive angles, negative angles. So what they're referring to there is, remember that if the initial side of your angle is on the positive x-axis, then your angle is said to be in standard position. But you can measure angles positively or negatively. So like if we start at the initial side and we go up 60 degrees, that's a positive 60. If we go down 300 degrees, we would have the same terminal side. That would be a negative 300. And that led to our ideas of coterminals, that negative 300 and positive 60 are 2 different names for the same angle. And the way that we find coterminals is we just add or subtract 360. If we're in radians, we add or subtract 2 pi. So on the bottom of page A25, they give you several examples there of coterminals and multiple names for the same angles and how we find those. All right, over on the top of A26, they start a parade of formulas. So top of A26, they remind us of the definitions of our 6 trig functions in terms of opposite, adjacent, and hypotenuse. So what they're referring to there is if you have a right triangle, on that right triangle, opposite your right angle is your hypotenuse. Here's your central angle, so opposite of that we call the opposite side, and then this is our adjacent side to that angle. So we can go through and define our 6 trig functions based on that triangle. That's like the Chief SOHCAHTOA thing that you learned all the way back in 9th grade. So we could say that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. We also had a word association for that last year. We used sophomore for sine, so sophomore, S-O-H, S-O-H. Cosine we used cash, so cash was C-A-H. And tangent we used toad, so toad was T-O-A. Then their reciprocals, the reciprocal of sine is cosecant, so you can see that we just invert our identity. The reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. We don't seem to have trouble remembering tangent and cotangent, but it's easy to get these mixed up. So the thing we said last year is that in every reciprocal pair, there's one S and there's one C. So sine starts with S, cosecant starts with C, cosine starts with C, secant starts with S. If you accidentally put these two together, you would be like, wait, there's two that start with S, something's wrong. Once we defined them based on a triangle, then we went back and we redefined them based on a circle. And we said, okay, if I took this triangle and I inscribed it into a circle, then my adjacent side would be laying on the x-axis. My opposite side would be the same thing as my vertical value, my y value, and my hypotenuse would go from the center of the circle to a point on the circle, which we know to be a radius. So if we went back and defined these, anywhere adjacent became x, opposite became y, and hypotenuse became r, then that created these 6 new definitions that we utilized. We also knew that tangent was sine over cosine, and the reciprocal then of that would be cosine over sine. So those identities there on the top of page A26. Now, if you happen to have a unit circle where your radius is 1, and that's not always the case, but if it's a unit circle with a radius of 1, then each of these r's go to 1. And so in a unit circle, sine is just the y value and cosine is just the x value. And of course, their reciprocals would follow suit. So that led us to our first quadrant that we worked with all of the time. And so the little shortcut way that we had of building this was we started with 0, and we would start and look at the numerator. So sine counts up. It goes 0, 1, 2, 3 in the numerator, and cosine counts down, so it starts with 0, 1, 2, 3. So once I built those numerators, then it laid out for me exactly what values went where. Then remember that tangent is just the sine value, 1/2 divided by the cosine value, square root of 3 over 2, all the way across. And that's how we built those first quadrant values that then we could utilize. Additionally, over on the bottom of page A26, they give you those values that we were just referencing there. They have it in a table form, whereas we have it laid out on the first quadrant. Top of page A27, they remind you all students take calculus to determine where your quadrants are positive and negative. So when we say students over here, that tells me that S is the second quadrant, and that means that only sine in the second quadrant is positive. So in the first quadrant, all of them are positive. Second quadrant, only sine. Third quadrant, only tangent. Fourth quadrant, only cosine. When we say, for instance, in the second quadrant that only sine is positive, we're referencing the primary 3 trig functions. We're not saying that its reciprocal cosecant is negative there. The reciprocals go along with the originals. So we're just talking about sine, cosine, and tangent when we're building that chart. All right, so finally, an example. Example 3. All right, example 3 says, find the exact trig ratios for theta is equal to 2 pi over 3. So if my central angle is 2 pi over 3, what are the 6 trig values? What are sine, cosine, tangent, secant, cosecant, and cotangent? And they want the exact answer. So they don't want me to type sine 2 pi over 3 in my calculator. They want like square root of 3 over 2, 1/2 square root of 2 over 2 kind of stuff. Okay? 2 different ways that we can do this, depending on whether you base it on a triangle or you base it on a circle. So I'll remind you of both ways. The first way is if I wanted to draw the triangle, I could say, okay, where's 2 pi over 3? I literally could draw over to 2 pi over 3 and say, okay, let's draw the triangle that goes along with that. So my reference angle, my distance away from the x-axis, you can see there would be 1 pi over 3. That's a 60-degree angle. And this is a right triangle, so my right angle is here, so this would have to be a 30-degree angle up here. We learned 30, 60, 90 triangles in geometry, so we're very proficient with those and the relationships of their sides so that we could define the values of their sides, because it doesn't matter what the length of x and y and r might be, the ratio is going to be the same in a 30, 60, 90 triangle. So I could go through then and define my x value, my y value, and my r value in that way. Because I'm in the second quadrant, I would know that only sine was positive, and so I would make my cosine value negative because it coincides with x. Or I could think about over here my x values are negative and my y values are positive. Radius is always positive. So based on that, I could use the definition of sine and say sine is y over r. So that would be square root of 3 over 2, and I would get my value. And I could do that with all 6 of the values by using the triangle. I think most of us, instead of using the triangle, got to the place last year that we much preferred using the values from the unit circle. And so if I were using the values from the unit circle to do that problem, I would start by saying, what's my reference angle? Remember that if it is a multiple of pi over 3, pi over 4, or pi over 6, that is the angle that you're given, you literally can look at it, and that pi over 3 will be my reference angle. So I've got my reference angle. Now I could come up and say, okay, looking at my chart, here's pi over 3. So I can look at this and say, okay, my sine is going to be square root of 3 over 2. My cosine is going to be 1/2. My tangent is going to be square root of 3. And I would get all 3 of those values like that. Then I would just flip them to get their reciprocals, being sure that I rationalized anywhere that I needed to. Now, that gave me the values. I still have to go back and figure out, are these positive or negative based on the quadrant that I'm in? So we've already talked about the fact that we're in the second quadrant, and in the second quadrant, only sine is positive. So I would go back and say that sine and its reciprocal cosecant are positive, but everything else would be negative. So there in the middle of A27, they give you those key values for sine and cosine from around the unit circle. What if the value that they give me, however, is not a unit circle value? Like example number 4, they tell me cosine is equal to 2/5. That's not one of the values that I know off the circle. In that case, I don't have a choice between circle and triangle. I have to go back to building a triangle. So I can go back and say, okay, if cosine is equal to adjacent over hypotenuse, or x over r, then I know the relationship of a right triangle is a squared plus b squared equals c squared, Pythagorean theorem. I could say that x squared plus y squared is equal to r squared. So let's plug in what we know. We know that x is 2, and we know that r is 5, and that'll enable us to figure out what y is. So what are we going to get for y? Square root of 21. It could be positive or it could be negative, because when I insert a square root, I always insert a plus or minus. That is going to come back to the quadrant that I'm in, so we'll catch that in just a minute. So now that I know that x is 2 and y is the square root of 21 and r is 5, then I can use these definitions, or if you would rather write them as adjacent, opposite, hypotenuse, that's fine. I can use those definitions to go through and figure these out. So I could say, okay, if sine is y over r, then I'm going to take my y value, square root of 21, and put it over my r value, 5. Cosine was the given value. It was 2/5. And what would you get for tangent? Square root of 21 over 2, exactly. And then we can use the reciprocal identities to just flip those, being sure that we rationalize where needed. So once I have my values, I still have to go back and figure out if these are positive or negative based on the quadrant that I'm in. So if I go back, they will have to give me some information about the quadrant. In this case, they told me that theta was between 0 and pi over 2. What quadrant is that? So if I'm in the first quadrant, everything is positive. So yeah, all those values would be positive. All right, then example number 5. Example 5 says, use a calculator to approximate the value of x in figure 12. And here's what they gave you for figure 12 in the book, this little guy right here. So if I'm looking at that figure, whether you look at it in the book or you look at it up here, I don't think it's there on your sheet, or it may be partially chopped off kind of thing. But in any case, we have this angle. We know what's opposite of it, and we know what's adjacent to it. So which trig identity do I use? Tangent, right. So I could use tangent of 40. Since tangent is opposite over adjacent, what is opposite? 16. And what's adjacent? X. All right, how am I going to solve that for x? Yes. Yes. I'm going to cross multiply or multiply both sides by x, and then, yes, divide the 16 by tangent 40. Now, they told me to throw this into my calculator. Do you need to be in degree mode or radian mode? Degree mode, because I've got 40 degrees down here, but watch, because you know we always had to flip back and forth all the time with that. And when I type that in the textbook, the answer that they give is 19.07. That would be wrong on the FRQ questions on the multiple choice. You would not get credit for that answer because it is only 2 decimal places. So we're intentionally going to strive to consistently use 3 decimal place accuracy. Okay? All right, so here is our homework for tonight. On page A32, we're doing 1 through 37, every other odd, number 12, number 15 in addition, and then challenge 43.